Welcome to the 6th pre-recording of the Programming Languages Virtual Meetup. My name is Connor Hoekstra, and in this pre-recording, we're going to be covering the second half of part 2 of chapter 2. So in the last video, 2 weeks ago, we covered the first half. That was sections 2.2.1 and 2.2.2, representing sequences and hierarchical structures. In this pre-recording, we're going to be covering the final 2 sections of this chapter, hierarchical data and the closure property, those sections being 2.2.3 and 2.2.4, sequences as conventional interfaces, and example, a picture language. Most of it will be spent in 2.2.3, so let's hop into it. One of the first examples, or 2 examples, that this chapter introduces to us is the following: a procedure called sum odd squares that, given a tree, takes all the odd valued leaves of the tree, squares them, and then sums them. And then it introduces to us a second procedure called even fibs, which creates a list of the first n even Fibonacci numbers. And it shows these 2 procedures as sort of hand-rolling everything. And once it talks a bit about this, it then goes on to show us that it's easier if we separate out the individual components of each of these procedures. And it has this visualization of the following. So for the first procedure, where we are squaring and then summing all the odd leaves of a tree, we first need to, from our tree, get the leaf values. Then we need to filter out the odd ones, or filter out the even ones, filter in the odd ones, then square all the values and then add them up. And for our second procedure, we have to enumerate all the integers, then turn these integers into Fibonacci numbers, filter in all the even ones, and then put those into a list. And the point that the authors are making is that even though at face value, when you look at these procedures, they don't seem to have much in common, when you filter out the individual components, they all are basically made up of enumerate, map, filter, and accumulate. And the authors state, in sum odd squares, we begin with an enumerator which generates a signal consisting of the leaves of a given tree. The signal is passed through a filter which eliminates all but the odd elements. The resulting signal is in turn passed through a map, which is a transducer that applies the square procedure to each element. The output of the map is then fed to an accumulator which combines the elements using plus, starting from an initial 0. The plan for even fibs is analogous. And they go on to say, our 2 procedures decompose the computations in a different way, spreading the enumeration over the program and mingling it with map, the filter, and the accumulation. If we could organize our programs to make the signal flow structure manifest in the procedures we write, this would increase the conceptual clarity of the resulting code. So pretty cool that the authors are just pointing out that making use of abstractions and algorithms increases the conceptual clarity of our resulting code. And so they go on to show that for the sum odd squares example, if we make use of accumulate, filter, and enumerate tree, we can basically simplify our code to the following. And if you've been watching all of these recordings or pre-recordings up until now, you are probably anticipating what my next slide is going to be, and that is a reorganizing of our code to make use of the threading macro, which in my opinion is way more readable, way more beautiful, and even highlights more the conceptual clarity we get when we make use of these algorithms, filter, map, and accumulate. So we're just calling these in the order that the authors mentioned in the book. We're first enumerating the leaves, then filtering out the even numbers, so keeping the odd ones, then calling a map and squaring each of those, and then doing a reduction, or what this book calls an accumulation, or an accumulator, making a call to the function accumulate. So pretty cool. And there's a footnote that I absolutely loved. It states, Richard Waters developed a program that automatically analyzes traditional Fortran programs, viewing them in terms of maps, filters, and accumulations. He found that fully 90% of the code in the Fortran scientific subroutine package fits neatly into this paradigm. One of the reasons for the success of Lisp as a programming language is that lists provide a standard medium for expressing ordered collections so that they can be manipulated using higher order operations. The programming language APL owes much of its power and appeal to a similar choice. In APL, all data are represented as arrays, and there is a universal and convenient set of generic operations for all sorts of array operations. So Once again, if you watched the previous pre-recording, I got pretty excited when in the MIT lecture, I believe it was 3A, Hal Abelson called out the power and elegance of APL. And now, once again, this time in the text, APL is being mentioned. And APL, it's one of my favorite languages, if not my favorite language, because you can just write some absolutely beautiful code that is extremely powerful and extremely terse. So at this point, we jump into our first exercise, exercise 2.33, fill in the missing expressions to complete the following definitions of some basic list manipulation operations as accumulations. So it's basically asking us to define map, append, and length using or in terms of accumulate. So on the next slide, we have our solutions for accumulate. Note that accumulate is a fold right, not a fold left. So because it's a fold right, the way it's defined in the book, we can just make a call to a lambda, and then inside our lambda, make a call to cons, which is basically going to perform our procedure P on each of the elements X, and then cons it with our accumulator, which is exactly what we want. For append, all we have to do is make cons, initialize this to seek1, and then pass it seek2, which it will element by element cons on. So basically just the difference between map and append here is that our initial starting point for our accumulator is an empty list, whereas for append, it is our sequence 1. And last but not least, length. This is a very common example for sort of trying to understand recursive functions or accumulations. Here we can define length by, in our lambda, throwing away each of the values that we are sort of quote unquote looping over, and then just adding to our accumulator 1 for every element that we visit. So we can use the underscore or the underbar here to communicate that we're not going to be using the value. We only need the accumulator here. And note that because accumulate is a fold right, the accumulator is on the right, not on the left. Our next exercise, this is sort of complicated. It sounds complicated when you read it, but it's actually pretty straightforward. It says evaluating a polynomial in X at a given value of X can be formulated as an accumulation. We evaluate the polynomial, read that expression, using a well-known algorithm called Horner's rule, which structures the computation as the following. So it's basically recursively multiplying your accumulator by X and then adding the current coefficient. And then you just continue to do that. In other words, we start with an, multiply by X, and then add an minus 1, and so on and so forth. And then it asks you to fill in the following template in order to get this behavior. So it gives you most of the code, and you just need to fill in the 2 question marks here. And if we do this, we end up with the following. So we're making a call to accumulate. We have our lambda that is taking an accumulator for the second parameter, as this is a fold right, and then our coefficient. And as we saw, we basically just want to multiply our accumulator by X and then add the current coefficient. That's exactly what we're doing. So multiplying X by our accumulator and then adding our coefficient, and we're done. The next exercise, 2.36, the procedure accumulate n is similar to accumulate except that it takes as its third argument a sequence of sequences, which are all assumed to have the same number of elements. It applies the designated accumulation procedure to combine all the first elements of the sequences, all the second elements of the sequences, and so on, and returns a sequence of results. For instance, if S is a sequence containing the 4 sequences 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, then the value of accumulate n plus 0s should be the sequence 22, 26, 30. Fill in the missing expressions in the following definition of accumulate n. So once again, this chapter this question giving us most of the definition of this procedure, and we just need to fill in the question marks. So we're essentially performing an accumulation across each of the indexes of the given lists. So we have 4 sublists here, and we want to add each of the first elements, each of the second elements, and then we end up with the following list. So in this definition, it's actually pretty straightforward. We are just consing an accumulate operation to all of the first elements of our list of lists sequences here. So we're just mapping car over seeks to basically get the first element from each of our sublists. And then we're applying this operation and init with accumulate to get the value. So in the case where we were adding these up, we're then going to add, starting from 0, all of the first elements of the lists. And then we're making a recursive call to accumulate n, where we're ferrying along op and init to do the next time we need to accumulate. And then we're calling cdr and mapping this over seeks to basically drop the first element so that we can continue to do this on each of the first elements for the subsequent recursive calls to accumulate n. And here's a little example here, 0, 1, 1, 2, 2, 3. If we add up each of the indexes, we're going to get 1 plus 2 for 3, and then 1 plus 2 plus 3 for 6 for the second element. So might be a bit tricky to wrap your head around, but once you understand it, it's actually pretty straightforward. And so what's interesting is that they call this out, or procedure in the book, accumulate n. But it's actually known, what I thought was the most common name for this algorithm, zipwith from Haskell. But when I had never done what I call sort of my opponent research, where I go to other languages and try to track down what each of the names of this algorithm is in different languages. Haskell was actually the only language I could find that was calling this algorithm zipwith. C++ has a 2-range version of their transform algorithm that you can use. So it doesn't go up to n, it just goes up to 2. But in theory, you could have a n-ary version of transform that did the same thing. Same thing with zipwith for Haskell. It only takes 2, but there's also zipwith 3, zipwith 4. And then for the other languages, they all basically call it map. So Clojure and Racket, they call their algorithm map, and so you can do this to map over a single sequence, but if you have multiple sequences, it's just going to take the operation and apply it to all of them. So for a single sequence map, you need a unary operation. For a 2-sequence map, you need a binary operation, so on and so forth. And OCaml and F#, they don't have sort of the variaticness of the Clojure and Racket map, but they have explicit map2 functions, which take 2 sequences. So interesting that this book chooses to call it accumulate n when most other functional languages actually call it map, because you hear the 3 most common functional programming procedures or algorithms are map, filter, and reduce, and accumulate is another name for reduce. But in most functional programming languages, they actually call this map. So just an interesting piece of trivia. The next question is exercise 2.37. I'm not going to read through all of this. It's basically asking us to define 3 or 4, because I guess it gives us one solution. So it's asking us to define 3 procedures that do the following. One is transpose, and the other does matrix multiplication, and the other one does matrix vector multiplication. And it gives us dot product, which in some languages is called inner product, which basically just takes 2 vectors and then does a zipwith or an accumulate n. So interesting that they don't use accumulate n here when they technically could, but I guess accumulate in this case just works as well. And they're mapping over these values multiplication. So you're just taking 2 sequences and then multiplying the corresponding elements. So this question, once again, gives us most of the definition of these procedures. We just need to fill it in. This is the dot product one that they gave us. So if we pass it the value 0 to 3, it's going to end up basically squaring each of those values. So we're going to end up with 1 plus 4 plus 9 is going to give us 14. For our next procedure, matrix times vector, we basically just need to call a lambda and then perform the dot product on each of the rows of our matrix. So pretty straightforward. For transpose, this one is, I think, really important to wrap your head around. You are basically just concatenating all of the elements when you're calling accumulate n. So instead of doing your quote-unquote reduction on each of the indices, you're just concatenating them all together, which effectively is doing a transpose, which is when you flip it on sort of the 45-degree angle. And last but not least is our matrix multiplication, similar to our matrix vector multiplication, where we were calling the dot product on each row. This one we just need to call the matrix vector on each of our rows. Important, I think, to sort of understand these examples, because if you can understand these, I think you're basically getting the essence of what this chapter is covering. And one of the next procedures that the book shows us is a procedure called prime sum pairs that asks you to generate a list of pairs where the sum is prime and I is less than j. And it shows how, once again, if you make use of these built-in, very common algorithms, map, filter, enumerate, and they also introduce flat map, you can end up with very clear code compared to what you would end up with if you just hand rolled this all by yourself. And this is sort of what they're asking us to do in the next couple exercises. So exercise 2.40 states, define a procedure unique pairs that, given an integer n, generates the sequence of pairs ij with I less than or equal to j less than I less than or equal to n. And we didn't do the last part of this question, so we're just focusing on the first part here. And here we're making use of, once again, algorithms, threading, and some built-in racket functions. So the first thing we need to do in order to generate our pairs is we need to generate a range of the numbers from 1 to n. Note that range is exclusive, so we have to add 1 to n. Now that we have our list, we can make a call to a racket algorithm called Cartesian Product, which is going to generate us every single combination of the elements from each of our lists. Here the list is the same. Then we're filtering out the elements where j is greater than I, because we only want the ones where they are in increasing order. So we make a call to filter increasing, and then we just remove the duplicates. So extremely beautiful, in my opinion, when you make use of algorithms and threading. And due to the fact that APL has been mentioned twice in this chapter section, once previously in the MIT lecture and then once in the footnote, this is the APL solution of the problem that we just covered. And at the end of the video, I'll do like a walkthrough of showing you how we can build up to this solution. The next exercise is exercise 2.41. Write a procedure to find all ordered triplets of distinct positive integers I, j, and k less than or equal to a given integer n that sum to a given integer s. So similar to our last solution, which relied on algorithms and threading, this solution is going to be the exact same. So it looks pretty similar. We're generating our range of numbers from 1 to n the same way. We're making the same called the Cartesian product, but because we want ordered triplets here, we now need to take all the combinations of the values from 3 lists, not just from 2. So we're passing 2 lists here, and then this one's going to get bound to the end. We then do the same thing where we filter out all the non-increasing sequences of 3 elements. And once we've done that, we just need to filter out the elements that don't sum to k. So here we want to filter in for our triplet of numbers. If we sum this up and it's equal to k, we want to keep it. And that's it, you're done. And at this point, we move on to the final section, which talks about this picture language. We're not going to spend a ton of time, but I do highly recommend going and working through all of the exercises. But basically, the section shows how you can generate these non-trivial posters or pictures by building up level by level to these algorithms called beside, below, above, etc. And those make use of sort of algorithms at the level below, which make use of algorithms at the level below, which are just basically all cons and cutter at the end of the day. So it's pretty neat to see how you can end up with these images. It shows a couple other diagrams of how you can make use of things called wave to sort of reorient and scale these pictures, and how you can, using recursion and combining all these things, you can get neater pictures. So we're only going to cover the first 2 exercises from this section, but it starts to give you an idea of what we're working up to. So the first exercise from this section is 2.44, and it says define the procedure upsplit used by corner split. It is similar to right split, except that it switches the roles of below and beside. So this is the declaration of our procedure upsplit. It's going to take a painter, which is essentially just an image, and then n, which is the number of times you want to recursively split the photo and then sort of align it on top. So if we look at the call to upsplit here, we basically start with our painter. If we're given 1, you're just going to end up with that image. So here we're passing it Einstein, which is an image that the SICP picked language comes with. And if we make a call to 2, it's then going to basically split this twice, and then we make a call to 3. So I guess actually maybe upsplit 1 gives you 1 split, and upsplit 0 would just give you the image by itself. So when we make a call to 2, it then does this recursively again, and the 3 is the top row here. And right split's the exact same thing, but like it says, instead of using below, it used beside. So the solution to this problem is the following. We have both upsplit and right split next to each other. As mentioned, if n is equal to 0, you just display the image. Otherwise, in a let binding, you define smaller to be a recursive call to painter, and then you are decrementing n. So this is where you're going to be basically putting images next to each other and below each other. And as you do this, it automatically halves the size of the image because of the next line. So when you go beside smaller, smaller, below painter, it puts the initial image at the level that you're at below, and then the 2 images above it. And because there's 2 of them, they'll get halved in size. And then you're going to recursively do this until you work your way down into the base case, and you're just ending up with n equals 0, and you're returning the painter. Right is basically the exact same. Instead of a recursive call to upsplit here, though, we have a recursive call to right split, and the beside and the below are swapped. And that leads us to our final exercise that we're going to be covering, and it states, exercise 2.45, right split and upsplit can be expressed as instances of a general splitting operation. Define a procedure split with the property that, evaluating the 2 following procedures, produces procedures right split and upsplit with the same behaviors as the ones already defined. So pretty straightforward if you've been following, because we've had exercises like this before in chapter 1. So the abstract version, which we're calling split here, just takes 2 operations f and g, and then due to the fact that we're going to need to recursively call this, we need to define an intermediate function, which we'll just call rec for recursive, which takes our image painter and our value m. And then the body of this is basically the exact same as what we saw for upsplit and right split, except now we've replaced upsplit and right split with rec, and our 2 operations f and g, which used to be beside and below, are now replaced. And at the end of this, we just need to return rec. So this is going to be a higher order function because we're returning a function, or procedure, I should say. And then at the bottom, as we saw before, we can just define right split as split beside below and upsplit as split below beside. So pretty straightforward. And I believe I only have one thing I wanted to highlight from the second half of the lecture 3A from the MIT lecture, which is just sort of a Easter egg for the C++ programmers that are watching this online, and that is that at one point Hal Abelson mentions there's an operation called rotate, and if you're a C++ or programmer that watches CPPCon talks or C++ Now talks, you will all know that we all have a special place in our hearts for rotate. Although I should mention that the rotate Professor Abelson is referring to is one that rotates a picture a certain number of degrees, whereas the rotate in C++ is slightly differently. But I believe that's it for everything I wanted to show from the MIT lecture. So now we'll hop over to my APL terminal and we'll walk through the example that I mentioned earlier. So let us work through the APL solution to the unique pairs problem that we saw earlier. So we read our expression from right to left. First, if we generate this, it's going to generate all unique pairs with elements less than 4. where the two numbers, the one on the left is less than the one on the right. So that's 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. And because we start on the right, we will just look at iota 4. That basically just generates us a list of numbers 1 to 4. The next algorithm we need to use is something called outer product. And this, given a list of elements on the left and a list of elements on the right, plus a binary operation, will perform that binary operation on every single pair of elements that you can generate from those two lists. So in this case, we want to just create pairs. So we're going to use something called catenate. Then if we provide an iota 4 on the left and iota 4 on the right, we then end up with a table, a 4x4 table of all the pairs. Note that if I were to replace this catenation with a plus, it's just going to add the numbers together. If I replace this catenation with a multiplied, it's going to multiply the numbers together. Hopefully you get the idea. Note that you might have noticed in my expression I didn't have two iotas, and that's because they have a special algorithm called switch, or an operator called switch, which means apply the argument on the right as the same for the argument on the left. So this is the equivalent of using two iotas. So here we have our two-dimensional table of numbers. At this point, we want to flatten our table into just a single vector, and we can use the unary version of our catenate. So this is a binary operation. This is a unary operation, meaning this one only takes one argument on the right. And when you only have one argument for the comma, it becomes something called ravel, which is the equivalent. That is not what I wanted. It becomes the equivalent of flatten, or what is called flatten in many languages. At this point, we will save this in T, and we basically just need to filter out any of the pairs that are not in increasing order. So in order to do this, we can make use of basically the filter algorithm, which is called compress in APL. And what you do is you give your elements that you want to do some filtering on the right, and then you pass it a Boolean vector of ones and zeros, and anything that corresponds to a 1 will be kept, and anything that corresponds to be a 0 will be filtered out. So an example of this, if we have 1, 0, 1, 0 with iota 4, or 1, 2, 3, 4, you're going to keep the 1 and the 3, and then get rid of the 2 and the 4. So in order to generate a Boolean vector of ones and zeros that represent the increasing pairs, we can use basically a less than reduction over our vector t. And if we do this, we get a Boolean vector where the ones correspond to all the elements that are in increasing order. So if we combine this now with our t, we have our answer. And so basically we just need to, oh, that was the one I wanted. We can basically just add what we had, what we just saw, to the following, and that is our solution. And if we want to make this generic and call this unique pairs, we can put this basically in a function, and omega here means the first parameter, and for this we only need one. So now the next time, if we want all the unique pairs from, I guess that was too many to show all on the same screen, so we can just do this with 6. Hopefully that's not too many. We get our answer. So hopefully you found this cool. If you're interested in APL, just Google Dialog APL. You can download it for free. And it's an extremely impressive language. You can do really cool things with it. That's it for this week's pre-recording. Thanks for watching. I hope you enjoyed, and we'll see you next week.